Welcome to problem solving session for Introduction to Group Theory course. I'm Siddhi Ambure from IIT Gandhinagar, and today we will discuss problems related to syllabus from week 12, that is problems related to structure theorem using invariant factors, and structure theorems of finite abelian P groups. So let us start with our first question. So the question asks for the automorphism group of Z10. So the question is, which among the following is the automorphism group of Z10? And the options are Z4, Z2 cross Z2, Z10, and Z5 cross Z2. Okay, so I hope you know what is group of automorphisms. And so what we have to find is group of automorphisms of Z10, and among these four groups here, to which it is isomorphic. So we have already seen multiple times that automorphism group of Zn is isomorphic to Un, that is group of units of Zn. So in this case, we have to find automorphism group of Z10. So this is isomorphic to U10, and we know U10 is what it is, all those n bar in Z10Z such that GCD of this n and 10 is 1. So this is 1 bar, 3 bar, 7 bar, and 9 bar. So for now we got that this is the automorphism group is, the cardinality of automorphism group is 4. Okay, so if at all it is isomorphic to any of these 4 groups, its cardinality must be equal to that group. Okay, so here cardinality of Z10 is 10. So definitely this one will not be isomorphic to group of automorphisms of Z10. Similarly, if I go for, if I check for this Z2 cross Z5 cross Z2, then cardinality of this group is also 10. So again, this will not be isomorphic to automorphism group of Z10. So we have to check between these two because these are the two groups which have cardinality 4, that is Z4 and Z2 cross Z2. So in short, it is, we have to check whether when we write Z4, it is cyclic group generated by, it is cyclic group of order 4. And this Z2 cross Z2 is isomorphic to K4. The plane 4 group, that is, it is generated by, it has these 4 elements. If I say it has 4 element E, A, B, C, where E is identity of a group, then A square, B square, and C square is E, and AB is C. Okay, you can, so we have to check this U4, that this U10, which of, so we have to check whether U10 is cyclic or not. If it is cyclic, then it will be isomorphic to Z10 cross, it will be isomorphic to Z4, and otherwise it will be isomorphic to Z2 cross Z2. So do we have any, so this is identity. So let us check what is order of 3 bar here. So order of 3 bar is, so order of every element in K4 is either 2 or 1. So if I find any element which has order greater than 2, I can declare that it will be isomorphic to Z4, because if it has to if it has to be isomorphic to this Z2 cross Z2, then order of every element here in U10 would be 2. Okay, so order of 3 is, if you check, so 3 into T is 9 bar. So this is not, so order of 3 is definitely not equal to 2, because 9 bar is not equal to 1 bar here. And then 3 bar into 3 bar into 3 bar, it is 27 bar, which is isomorphic to 7 bar, which is equal to 7 bar in Z10. So order of 3 is not 3. And now if you go for this, and now this is 7 3s are 21. So this 21 bar, which is isomorphic to 1 bar in Z10. So order of T bar is 4 here. Okay, so the moment I have element of order 4, I get that it is isomorphic to Z4. Okay, so among these two, we get that it is isomorphic to Z4 and not this group. Okay, so I hope this is understandable. So we had to find a group of automorphisms of Z10. And what we did was, so this is something which we have been using multiple times in the lectures. This one, that automorphism group of Zn is isomorphic to Un, and it has nothing to do with Zn here. Any group, so this is also isomorphic to automorphism group of X such that order of any cyclic group. Let me write it here. Oh, it is isomorphic to, let me write it here, Cn. This is not a standard notation, or even if it is, I don't know. But this Cn means cyclic group of order n. Okay, so this still holds for any cyclic group of order n. And we have seen that, so we just calculated that automorphism group of Z10 has 4 elements. So we had to check which among these first two will be my group, where to which this automorphism group of Z10 is isomorphic to. And we just saw that there exists an element 3 which has order 4. And since this is also a group of order 4, it is a cyclic group generated by this element 3 here. And we get that this is cyclic group of order 4, and that's why it is isomorphic to Z4. Okay, I hope this was okay so far. If not, please let me know. Okay, we will move to now next question. Question 2. What is the cardinality of the group of automorphisms of the group Z5Z cross Z5Z? Okay, so and options are 420, 440, 460, and D is 480. Okay, so we have to calculate this. So any ideas how? So note that here we can't use this argument of the here. So let me write here that here we can't use. See, I mean this is Z5 cross Z5. And order of this group is 25. Okay, but we can't use this aught of Zn isomorphic to Un. I hope here I wrote isomorphic. Yeah, isomorphic. That's okay. Yeah, and when I write this equality is here. And yeah, that's okay. Yeah, so what I'm saying is that we can't really use this. Just a second. Hello?
Hello.
Yeah, sorry. So we can't really use this UN isomorphic to UN isomorphic to automorphism group of Zn. When I write here Zn, let me just erase this. So this is the notation which we are following. So let me write that. Yeah. So we can't use this because this, if I call this G is not isomorphic to Z25. Okay, this holds only for cyclic groups. And so G here is not isomorphic to Z25 because every element in Z5 cross Z5 has order 5. Okay, you can check this that for all A in G, order of A is 5. Okay, this G is Z5Z cross Z5Z. Okay, so this is definitely because for all element A in G, we have order of A is 5. You can check that. So that's why this is something different. So what we can see here is what I need to find is to find that number of. So how many? So if phi belongs to aught of Z5Z cross Z5Z, then phi is then phi is Z5Z cross Z5Z to this Z5Z cross Z5Z, and I want this map to be and phi is bijection and group homomorphism. Okay, so if you see that if I this Z5 is a field. Okay, Z5 is a field of order 5. So what I can do is, so this is what this is. So then this Z5 Z cross Z5Z, this becomes vector space of dimension 2 over Z5Z, right? Because this is generated by 0 bar comma 1 bar and 1 bar comma 0 bar over Z5. So this bijective maps here are basically uh, yeah uh, can be represented as matrices, invertible matrices in Z5. Okay, so what we are doing is, every phi from this, let me write this G, okay, denote G is equal to Z5Z cross Z5Z. So every phi from G to G can be expressed as 2 cross 2 invertible matrix with entries in Z5. Okay. Yeah, because we are looking at we are looking at these maps as a map of vector space over this field Z5. So what I need to find is, therefore, what we need to find is, what we need to find here is set of all invertible matrices Why 2 cross 2? Because this is two-dimensional vector space to two-dimensional vector space. That's why it's 2 cross 2 matrix. Okay. Invertible matrices. Yeah, just 2 cross 2 invertible matrices over Z5. When I say over Z5, so what I want to do is, I want to basically find this GL2 Z5Z. This is all ABCDs in M2 such that determinant of this determinant will be non-zero, and yeah, or we can say that this is invertible. So we have just asked for number. I mean, yeah, so the first one starts with 420, so we can't give expression for 420 elements anyway. But yeah, so we have to calculate how many how many such elements exist in this group. Okay, and we have to now do everything. Since we are in Z5, we have to take help of the fact that every element has order 5. Okay, so since I have to find 2 cross 2 invertible matrix, what I need to find is just two vectors in this Z5, two independent vectors, such that we get that their determinant will be non-zero, and the moment it is non-zero, I will get the matrix will be invertible because we are in field. Okay, so if I choose any element here in Z2 cross Z2, what are the options for me there? I mean, how many such elements I can choose here for the first row, right? That's how we find invertible maps in vector spaces over a field. So I need to find two columns in G or two elements from G such that they are linearly independent over Z5. Okay, so doesn't matter. Whatever I choose here, as long as it is the second column is not a linear multiple of the first one, I will get invertible matrix. Okay, so how many choices do I have here? So G has, see, this Z5 cross Z5 has 25 elements, but I can't have a column to be entirely 0, 0. That won't help me. That won't give me invertible matrix because then determinant will be 0. So I have 25 minus 1 choices for the first column. I can choose any column which is non-zero. So for the first column, I have 24 choices. Right. And then this one, this, so if I call this X here, so we need to find, so X has, if I call them X and Y, then X has 24 possibilities. Okay, and then if X is there, what will be linear span of X in Z over Z5? So linear span of this X here will contain definitely 0 bar, because what is linear span? When I say linear span, it is we are taking some element from Z5 and then we are multiplying it by this element X bar. Okay, and then this is, it will be of this sort. Then this will be 2x, 3x, 4x, and 5x, 1, sorry. Yeah, 1x, 2x, 3x, and 4x. When I write this, what I mean is this x will be some a bar comma b bar. So this is actually 0 bar comma 0 bar, a bar comma b bar, 2a bar comma 2b bar, 3a bar comma 3b bar, and this is 4a bar comma 4b bar. This will be the only possibilities which will give me which will be in the linear span of this element x here. This x is a bar comma b bar. Okay, so how many possibilities do I have for the elements which are not in the linear span of this first element x? So for not so this will be 25 minus these 5 elements, right? So possibilities for y are this 25 minus 5, that is 20. Note that here we excluded 0, 0, okay, but here when I'm looking at second column, I'm already 0, 0 is in span of the first one. So we are already excluding 0, 0 when we are choosing y. So that's why we don't have to again reduce the possibility. Okay, 0, 0 is already excluded when we are looking at the span of this x bar. Okay, so there are, for y we have now 20 choices. So, and since the moment I choose, so therefore uh, the number of or cardinality of GL2Z5Z will be this 24 into 20, and this will be 480. Okay, so this, so 480 is the last option. This is the only option which is correct. Okay, I hope this was okay and there are no doubts here for this one. I hope you understood. Please note that we can't use this automorphism group of Zn isomorphic to Un for any group. It has to be cyclic group. In this case, this Z5 cross Z5 is not a cyclic group because every element in Z5 cross Z5 has order 5. And Yeah. And second thing is, yeah, Z25 is a cyclic group which has element of order 25. So yes, these are the only things which I wanted to say for this. And in general, also, if yeah, if you this is how you can find. Yeah. So this is how you can find the cardinality of automorphism group of. So this is the answer then. Z5Z is 480. I hope this was clear. If you have any doubt, please let me know. This. I hope you understood why we chose here 20 and how we are choosing elements which are not in the span of Z5. You can always do this with the any ZP cross ZP. Where ZP is prime. Or in general, yeah, ZP is prime. And try to see what you can do in case of Zn cross Zn. And uh, yes, Zn cross Zn. And you can directly try to calculate formula for this, that what will be the answer here. Okay, I hope this was fine. And yes, now we'll move to the next question here. Yeah. Okay, so third question, that the exponent of the abelian group Z cross 2Z, let me write this below, Z cross 2Z cross Z cross 5Z cross Z cross 6Z is option is 10, 15, 30, and 60. Okay, so exponent of abelian group. So what is exponent of abelian group? So our definition, let me write this. The exponent of a group G is a smallest number let me write this as K, such that for all G in G, this G power K is identity of G. That is when I rate any element, or if I multiply any element this k times, I get that order of, I will get the identity element. That's the whole thing about this exponent of a group G. So that's what we have to calculate for this Z2. So here G is Z cross 2Z cross Z cross 5Z cross Z cross 6Z. And now we have to calculate what is the exponent of this group G. Okay, so first understand that this, so any element in G, sorry, looks like A bar, B bar, C bar, where A bar belongs to Z2Z, B bar belongs to Z5Z, and C bar belongs to Z6Z. So if when I say that exponent, I need to find, so we have to find K in N such that when I write this A bar, B bar, and C bar power K here, this power K is just group multiplication or group addition. Here we are in additive group. So this is K such that K A bar, that is K A bar, K B bar, and K C bar is 0, 0, 0. And this first 0 is 0 in Z2, second one is second one is in Z5, and third one is in Z6. So note that for this A and C here, if for C, if I want, what is order of C here? Or if I, okay, so what is exponent of Z6? Z6 is a cyclic group of order 6, right? So what is its exponent? So for any cyclic group, exponent is the order of that group. Okay, you can check that. So in Z6, exponent of Z6 is 6. Okay. And so if I want to make this final number here, or this third coordinate 0, I need to have this kc bar to be 0. And what k I will choose for this c to become 0? It needs to be 6. Okay, 6 or any multiple of 6. The moment I have 6, I can take any multiple and it will still give me 0 in that case. So this 6 must be there. And the moment I have 6, you can note that this 6a bar will also be 0. Okay, so for a bar in Z2, this 6a bar will also be 0. So the moment I choose this number 6, it takes care of this first coordinate and third coordinate in G, which will give me 0 there. So now I have to deal with this B bar. When will it be 0? So 6B bar need not be 0, right? Because we are in Z5. If I take 1 bar and take 6 into 1 bar, that is 6 bar, it is not 0 in Z5. So for Z5, what is exponent of Z5? Again, it is cyclic group of order 5, so it has to be 5. Okay, so if I want a number which makes both this, all three of this A bar, B bar and C bar, when I multiply them by this K, I get 0, then that needs to be multiplication or multiplication of these two numbers, right? Or the least common multiple of these two numbers, so that I will get this Ka bar to be 0. Okay, so therefore it is 5. So therefore this exponent, this we can choose K bar, therefore we can have K bar to be this 6 into 5, that is 30, but such that, sorry, not K bar, such that 30 into A bar, B bar and C bar will be this 0, 0, 0. And you can check this, right? Because if I take any A bar, B bar and C bar in G, then this 30 A bar, 30 A bar, B bar, C bar will be 30 A bar, 30 B bar and 30 C bar. So this becomes 0 bar here because multiplication by 2, multiple of 2. This is multiple of 5, so this becomes 0 bar, and this is multiple of 6, becomes 0 bar. Okay, so the only possible choice here is this 30. Note that 15 won't help me because, let me write it here itself. 50 won't, 10 won't help because 10 A bar, 10 B bar, 10 C bar. If I choose 10, then for 1 bar, if I take this element 1 bar, 1 bar and 1 bar in G, then here I get 10 bar, right? If I multiply it by 10. So 10 bar, 10 bar, 10 bar is definitely 0 in first two coordinate, but third coordinate, this is not 0 bar. Similarly for 15, 15 bar, if I take 1 bar, Z6, in Z6, it won't be 0. The third coordinate still will create a problem. And 60 bar here definitely would work, but in the definition of exponent, we choose the exponent of a group G, which is the smallest and such that I get this exponent of group such that when I add or multiply by this element K times, I get the identity element of that group. So that's why here I'm choosing this number to be 30 in general. And this 30 turns out to be LCM of this 2 bar, 5 bar and 6 bar. You can check this. Therefore, in general, you can check this, that exponent of, in general, if G is equal to Z cross Zn1 cross Zn2 Z, so on up to Zn Tz, then exponent of G is LCM of N1, N2, so on up to Nt. Okay, you can choose this. You can keep this in mind if you are planning on a given exam. And yes. So if you keep this in mind, we directly get that this is the exponent of group G in this case. Okay, so I hope this one was fine. Yeah, let's move to now next question. Yes. Yeah. Identity group. No, sorry, not identity. Identify the groups that are isomorphic to Z4Z cross Z12Z cross Z5Z. Okay, and the options are 4, 12, 5. Options are Z4Z cross Z4Z cross Z15Z. Second is Z12Z cross Z, yes, Z20Z. C is Z4Z cross Z60Z. And the final option is Z3Z cross Z4Z cross Z20Z. So first thing, when you tackle the isomorphism of finite group, if you want the moment, I mean, when you want to start with identifying uh, which among these groups is isomorphic to given group, such questions will be there. I mean, possibly, I mean, in assignment or in exams, there is high, I mean, there are chances. So if you come across such questions, what you need to do is uh, first check for the cardinality. If two groups are isomorphic, if two finite groups are isomorphic, they need to have same cardinality. That's the first thing. The whenever we talk about isomorphism, the map need to be bijective map. And in finite cases, if a map is bijective, the cardinality of both both domain and codomain must be same. So we are in a finite case right now. So the moment you see such questions, the first thing you can do is you discard the options which does not have cardinality equal to the given group. So that's our first aim whenever you see such question. And then we will move to next thing, that is what we learned in the course, that is the structure theorem. Okay, structure theorem or theorem which we learned is that let G be an abelian group of order n is equal to p1 power alpha 1, p2 power alpha 2, pt power alpha t, uh, and this weight of order n, and n is equal to p1 power alpha 1, p2 power alpha 2, and pt power alpha t be the unique factorization of n. Okay, then what we will do, then what happens first, that this G is isomorphic to G1 cross G2, so on up to GT, where cardinality of each of this GI is P1 Pi power alpha I, and second that each GI is isomorphic to Z power Pi alpha I1 Z, yeah, Zi alpha I2, so on Z Pi alpha ITI, where this alpha I1, alpha I2, sorry, alpha ITI is a partition of this alpha I. So this is the statement, and let us understand the statement before we start to answer the given question. The first thing is, the statements talk about abelian group G of order n. So the statement holds, the statement is for abelian groups of finite order. Okay, and what is say is that G is isomorphic to cross product of, see, if n, when I write it, n has this prime factorization, then I can with the t distinct prime, then this G will be isomorphic to this product of t such groups, and each of which is group of order Pi power alpha I, which is similar to what we have here. The Pi power alpha I is the divides my group Gi, and each Gi is isomorphic to this cross product Z Pi power alpha I Z. I mean, yeah, yes. So Z Pi power alpha I cross Z Pi power alpha I2 cross Z Pi power alpha Ti, where this alpha I1, alpha I2, and alpha IT is a partition of alpha I. That is, partition of alpha I means this alpha I1 plus alpha I2 up to alpha ITI is my alpha I. This is what partition of this group means. So what it says is, let us try to understand with it with a small example. So yeah, what we need to do. So for example, let's talk about let G. So we just are given that G is an abelian group of order n. So let G be a group, abelian group of order, suppose 8. Okay, so I need to write this primary decomposition, or sorry, the prime decomposition or prime factorization of this number 8. So what is 8 is 2 cube, right? The cardinality of G, let us call this n, is 8. It is 2 cube. Okay, so G, what they are saying is that now G, by this theorem, G is isomorphic to this Z. This G1. So okay, so we have only one prime here. So G1, where this G1 is isomorphic to this some G This G1 is isomorphic to Z. Here my P is 2, so it is 2 power alpha 1 Z. Oh, here I need to write this Z as well. I hope this is not much of a, sorry. But since we are following the notation, let me be consistent. Pi is Z, then this is Z, and this is Z here. 2 power alpha 1, yeah, alpha, yes, we only have alpha 1, alpha is 3 here, so it doesn't matter. And cross Z power some 2 power alpha TZ. Okay, so I am saying alpha 1 is just alpha here. So where this alpha 1 plus alpha t must be equal to 3, the exponent here. Okay, here I had the exponent alpha I, which adds up to this alpha I, which was power of pi. So what is partition of 3? So partition of 3 is are possible. So how to write partitions is, I will also do this for some, yeah. So first 3, then 2 plus 1, then 1 plus 1 plus 1. So in general, when you write partition of any given number, start with that n, then this n minus 1 plus 1. Okay, so for example, let me write this for 5, okay, so that you will get idea. Because so that you don't skip any number in between. Otherwise, it would be a huge mess if you miss on any partition in between. So the best way to write all the partitions, count all the partitions is do this. This 4 will be 5 will be 4 plus 1. So what is 4? 4 is 3 plus 1 plus 1, right? 1 plus 1. And 3 is now, okay, so yeah, 4 plus 1. And now I will go to 3. So it will be 3 plus 2, then 3 plus 1 plus 1. Now we'll start with 2. Okay, but when I write partition, all the numbers next to it must be decreasing. So 2 will be 2 plus 1 plus 1 plus 1. And this will be 1 plus 1 plus 1 plus 1 plus 1. Okay, so these are the only partitions of 5 are possible. So what you do is you decrease the first number and then write all the possibilities of the rest numbers. So for 5, after 5, I will write it as 4 plus 1. Okay, so with 4 being the first digit, there are no other possibilities possible. Then I will move to 3. So 3 is 3 plus 2. Okay, and then the next possibility is 3 plus 1 plus 1. And these are the only possibilities. I can't go further. So now we will go to 2. 2 plus what? 2 plus 3 times 1. Because every time I move to the partition, what I do is I decrease the number. Okay, so here, so corresponding power here of, so corresponding group here, this will be Z power 2 power alpha 1. Alpha 1, so this is my alpha 1, alpha 2, alpha t. So this is only 3 here. So 2q Z. So which is Z mod 8Z. Okay. The second one is, sorry, this Wait, this I will just shrink. The second group is this Z cross 2 square Z cross, yeah, Z cross 2Z. So this is Z4Z cross Z4Z. Sorry, Z2Z. And similarly, this last one is Z2Z, power is 1, Z2Z cross Z2Z. So these are the only possible groups we can have where a Abelian group of order 8 is possible. Okay, these are the only possibilities. So this is like we are classifying all the groups of prime power, or yeah, in this case, prime power. And in general, through structure theorem, what we do is we classify all the possible uh, groups of given order, all the possible abelian groups of given order under isomorphism. These are the only possible. So when I write this, these are the only possible, sorry, these are the only possible choices for abelian group of order 8. Either it will be isomorphic to Z8, it will be isomorphic to this Z4 cross Z2, or it will be isomorphic to Z2 cross Z2 cross Z2. Okay, and these are the only possibilities we get from the structure theorem. And so this was quick example where the group had only prime power. But how to deal with this when you have higher powers or more than two, what I say, more than two possibilities for, uh, or there are more than two primes which divide the given n. So for example, let me do that also. For let G be 108, that is, it is 2 square into 3 cube. Okay, so what is, you can check this. This is 12 nines are, right? Yeah. So this is 2 square into 9 into 3, that is 3 cube. So 100 at it is 2 square 3 cube. And from the structure theorem, by structure theorem, what I have is that this G will be isomorphic to G cross this G1. This is my P1 here. This is my P2. So G1 cross G2, where each Gi is isomorphic to G power alpha, sorry, P1, that was 2. Yeah, I mean, doesn't matter. This is Pi power alpha I1 cross G Pi power alpha I2, so not G, Z. Z, Z, and so on up to Z power Pi alpha IT Z. I hope this, yeah, alpha ITI, yeah, ITI. Because, so here where this, let me write this, that alpha I1 plus alpha I Ti is equal to, where this alpha I1 plus alpha I Ti is equal to, where this alpha I1 plus alpha I Ti is equal to, where this alpha I1 plus alpha I Ti is equal to, where this alpha I1 plus alpha I Ti is equal to, where this alpha I1 plus alpha I Ti is equal to, where this alpha I1 plus alpha I Ti is equal to, where this alpha I1 plus alpha I Ti is equal to, where this alpha I1 plus alpha I Ti is equal to, where this alpha I1 plus alpha I Ti is equal to, where this alpha I1 plus alpha I Ti is equal to, where this alpha I1 plus alpha I Ti is equal to, where this alpha I1 plus alpha I Ti is equal to, where this alpha I1 plus alpha I Ti is equal to, where this alpha I1 plus alpha I Ti is equal to, where this alpha I1 plus alpha I Ti is equal to, where this alpha I1 plus alpha I Ti is equal to, where this alpha I1 plus alpha I Ti is equal to, where this alpha I1 plus alpha I ty, I mean, I'm just repeating, is partition of alpha I. Okay, so here my alpha 1 is 2, and the possible partition for 2 is 2 and then 1 plus 1. And partitions, and for alpha 2 is equal to 3, the partitions are 3, 2 plus 1, and then 1 plus 1 plus 1. Just a second. So these are the possibilities. So when I say that the then possible groups are, so how to write the possible groups? So partition, and here are my groups. So how to do that? So with e- each of this ZPI, I can choose one partition for this alpha I, right? So how with the two, I can, yeah, with the two, I can club this 3, which will give me Z2 square, Z cross Z3 cube, Z, which is Z4 cross. Okay, so for now, I will be omitting this Z in the denominator. I hope you understand when I write this, what you mean here. 2 square, 3 cube. So this is Z8 cross, or let me just write this in the bookish notation. This is Z2 square cross Z3 cube. This is Z4 cross Z27. Okay, similarly, with this partition of 2, I can combine this partition of 3, that is 2, 1, and this will be again Z2 square cross Z3 square cross Z3. So this will be Z4 cross Z9 cross Z3. Okay, these two groups are different. Okay, you can check. And then this 2, I can again club with this 1, 1, 1. That is the third partition of my 2, that is, sorry, 3. That is this Z2 square cross Z3 cross Z3 cross Z3. Again, powers are 1, so it remains as it is. Okay, and now now again I have second possibility for the partition of 2. So it will be 1 plus 1 here, or that is that 1, 1 with 3. So this will be Z2 cross Z2 with Z3 cube, that is, sorry, that is Z2 cross Z2 cross Z27. Similarly, 1, 1 I can pair with this second partition of 3, that is Z2 cross Z2 cross Z3 square cross Z3, that is, let me just shift everything here. That is, this is Z2 cross Z2 cross Z9 cross Z3, and the final one is this. And these are the only possibilities. It is Z2 cross Z2 cross Z3 cross Z3 cross Z3. Okay, so these are the only possibilities. So for abelian group of order 108. Okay, these are not all cyclic groups. Yeah, the cyclic group of order 108 comes under this, the first group which we wrote here. The rest are non-cyclic groups, and you can check that none of them is isomorphic to other. Okay, you can check that. And how to check that is basically comparing the powers. or not the powers, the order of particular element in that group. What is the maximum possible order in this group? What is the maximal possible order in this group? And so on. You can continue and you can check that you get, you kind of get different order in, yeah, in almost all of these cases. And that's how we get different groups. Okay, so that's how we this structure theorem we need to understood. We need to understand. And now we have to check this where this Z4 cross Z4. I mean, wait just a second. So now I need to find. We have to check which of these are possible groups where Z2 this G is isomorphic to G is what? Let me just write again. Not here. So this is the example. So my G was, I will be using this notation. So notation Zn is this Z cross Z and Z. Okay. So group was Z4 cross Z12 cross Z5. Okay, and what is cardinality of, so this is definitely a abelian group of some finite order. So what is the order of this group? This is 4 into 12 into 5. So this is 2 square into 2 square 3 into 5. So this is 2 power 4, 3 into 5. And now what I need to check is, so for, again, one thing you can observe here that this group, when I write it here, let me use another color. This group, when I write it here, I can also, so note that this Z2 cross Z3 is isomorphic to Z6, right? So I can very well write this group, which actually is same or isomorphic to this Z2 cross this Z6. I'm clubbing these two elements here. Or wait. I can write this as Z6. And again, I can write this as Z3 cross Z3. You can't club Z3 and Z3. Okay, Z3 cross Z3 is not isomorphic to Z9. Okay, you can do this when the GCD of these numbers is 1. So you can club. And these two groups are similar under isomorphism. You can check that. And that's why when such elements are, so when we look at structure theorem, each, yeah, this, where is it? Okay, where did I write it? Yeah, each of this GI is some, it looks like P group. It's some group of order power of P, pure power of P. But when you look at these groups here I have example in the option, I have this group Z12 cross Z20, which more or less does not suit uh, the exact state, what the expression for groups given in structure theorems. So when they write this, they are basically clubbing such groups where the order of that I mean, we are just clubbing those groups, uh, which has GCD 1, order of those groups is 1, and so on. Okay, so that's what we are doing here. And wait, yes. So let us check now. uh, whether this is possible or not. So the first, if you check for the order of this group is 240. Order of G is 240 here. I hope this is 240. Yes, it is 240. Here order of group is 15 into 16, right? 10 for 13. Wait. Yeah, so this is again 240. And now this is 12 into 20, that is again 240. Here 60 into 4, that is 240. And the final one is again a group of order 240. Okay, so by structure theorem, if I have any group uh, which is wait, just a second. Yeah, we have to now compare whether this is possible or not. Okay, and so when we write this Z40, 240, what we have is, yeah, 240. It is, no, sorry. Yeah. S- This is 2 power 4, 3, and 5. So, so this is basically will be some G1 cross Z3 cross Z5 because, yeah. And here it is 1 and 1. Partition of 1 is just 1. So basically this group will be G1 cross this Z3 cross Z5, where this G1 is some Z power 2 alpha 1 up to, sorry, yeah, 2 alpha 1 cross Z power 2 power alpha 2 cross this Z power 2 alpha k, not alpha t, since we are following this, where this alpha 1 plus alpha 2 plus alpha t adds up to alpha. That is adds up to 4. Okay, so the first option is Z4. So what is partition of 4? I can have partition of 4 to be 2 plus 2 such that I get this Z2 square cross Z2 square into Z3 cross Z5, right? And then this will be isomorphic to Z4 cross Z4 cross Z3 cross Z5. Okay. And then, but not that this Z4 cross Z4 is okay, but I can club this Z3 and Z5 to get this Z15. Okay. And that's how I get that this first one is definitely a group which can be isomorphic to the given group. Okay. And now the next one. This is Z12 cross Z20, the second one. So I'm just writing it here. This is first option or A option. The B is Z20, Z12 cross Z20. And here I can again choose this partition of 2, that is 4, that is 2 plus 2. I can write this Z2 cross Z2 cross Z4 and Z3 and Z5. Sorry, Z4 cross Z4 and Z3 and Z5. And this will be anyway isomorphic. So if you remember, we did this H cross K cross this cross Hn is the external direct product or the direct product. We can have this H sigma 1 cross H sigma T, sorry, yeah, sigma N, where sigma belong to this Sn. So these HIs still hold the permutation, the cross product does not change the isomorphism. I mean, what I'm saying is that in short, this Hi cross H1 cross H2 is equal to H2 cross H1, the isomorphic to H2 cross H1. So isomorphism holds under permutation of groups in direct sum. Okay, and so that's why this Z2, this will be isomorphic to Z4 cross Z3 cross Z4 cross Z5. And then this had GCD1. So this Z4 cross Z3 will be isomorphic to Z12. And this will be isomorphic to Z20 here. And that will give me my second option, Z2, Z12 cross Z20. The next one is Z4 cross Z60. And for us to have that, yeah. So this is again the extension of what we had in earlier example. It is this Z4 cross Z4 cross Z3 cross Z5 is isomorphic to this Z4 cross Z4 cross Z3 cross Z5. And since GCD of all these 4, 3, 5 is 1, I get that this is, if I take product of this is Z60. And similarly, the D section, the D option, it is Z3 cross Z4 cross Z20, and that is just this Z3 cross Z4, the similar one, this here. And I'm now shuffling this to Z3 as it is, Z4 as it is, and now I'm multiplying, I'm taking together this Z4 and Z20, which will give me this Z20. So in short, what we get is that all these 4 groups which are given here are isomorphic to my given group Z4 cross Z12 cross Z5. And yes, so the So this group has group that is this. I mean, it will have this all the four groups will be isomorphic to this given group. And but structure theorem also says that it gives the explicit expression, and we'll see in the next example again, like how this is happening. Let us just check this once again. Okay, so question 5. Okay, identify the groups that are isomorphic to Z24. Let me just write this. Z24 cross Z12 cross Z10. Okay, and the options are Z3 cross Z4 cross Z3 cross Z8 cross Z10, and B option is Z30 cross Z15 cross Z3 Z3 Z4 Z15 Z8 Z6 cross Z2, and the final is Z2 cross Z3 cross Z4 cross Z120. Yes. So how to proceed with this? Okay, so yeah. So given this G, so let us denote this G. So cardinality of G is 24 into 12 into 10, that is into 3 into 2 square, 2 into 5. I hope that's correct. Yeah. And this is 2 power 6, 3 square into 5. Okay, so we have to start checking for this isomorphism. So now, as I said, check for the orders. Here, this group is of order. Let me just calculate this. And here, this group has order 9 into 4. This is 3 square into 2 square into 2 cube into 2 into 5. So this is 2, 6, 3 square and 5. Here this is 2 into 3 into 5 into 3 into 5 into 3 into 2 square. That is, I have 5 square here. So this will not have order same to this. So note that first of all, the prime factorization of a given number is unique. So if you want to check whether two numbers are equal, the best way is to check their prime factorization. So instead of multiplying all these numbers, since these are small numbers, just write their prime factorization and check whether we have the same number of, whether those prime factorization coincide or not. Okay, so that's what I'm doing here instead of multiplying these things. Okay, so 2 cube, 2 power 6, 3 square, and 5 is the prime factorization of cardinality of G. And that's what I will be checking here, whether I have 6 powers of 2, 2 powers of 3, and 1 power of 5 there or not. The moment I have any of the mismatch, the cardinality of the given group will not be equal to the cardinality of, the cardinality of group from the options will not be equal to cardinality of this G. So that's what I'm doing here. So this is 3 into 5, 2 cube, 2 into 3 into, 2. So this has, this has one less of a 2. These are only 5 twos. So this will not be possible. And as you said, so 5 square, so not possible. And now the third one, let us try to, the fourth one. Here this 2 into 3 into 2 square into 120 is this 12 into 10. So that is 2 power 6, 3 and 5. Yeah, this is equal. 12 is 2 square into 3. So 3 and 5, and this 3 and 2 from 12, 1 from 10, I get 6 twos. So these are the number possible. And yes, and so these two have cardinality equal. So the first option, so this Z3 cross Z4 cross Z3 cross Z8 cross Z10, this has cardinality equal to cardinality of G, and this one has cardinality equal to G. So again, by structure theorem, we get that these two will be equal. Okay, so what I'm saying here is that if the moment I have cardinality is equal, the structure theorem is purely based on the cardinality of a group. Okay, and it gives us what are all the possible ways, what are the possible isomorphic groups of abelian groups of that order. Okay, and what we observe here is that the moment two groups have same cardinality, the under structure theorem, uh, there is a possibility that those will be uh, it could be possible. uh, it will, what I was saying is that which groups are isomorphic to the given group. Wait. That's not actually true. See here, thing that plays role here is the what I was saying is the exponent of the group G. That's what plays role here. Because see, and we saw that in the example that exponent is what will give me isomorphism in this case and not the cardinality. And when we did this clubbing of this similar GCD element, GCD1 elements, what we essentially did was uh, we kept the exponent of that group intact. We did not disturb that. Okay, that's why we could do it. The moment, so when I clubbed this Z3 and Z5, the exponent still remained 15. When I clubbed this Z4 and Z3, the exponent still remained 12 in that case. Similar, this one, I mean, the exponent of this group and this actually remained same. So what important is that we need to actually check exponent of the group in order to check whether given group is isomorphic to the groups given in the options. Because if I take this, so if I take some other partition of this group here, what was my example? Example has cardinality 240, right? In earlier case, it was 240. And if I take this group, Z2 cross Z2, so its power 2 power 4, 3 and 5. 2 power 4, 3 and 5. Wait. And if I take this group Z2 cross Z2 cross Z2 cross Z2 cross Z2, the 4 are there, then Z3 cross Z5. Then every element here has order. Yeah, this is 2 power 4. Yeah, this is 2 power 4. This is 3 and this is 5. Here order every element of this group has order LCM of this is 2, 3, 5. This will be just what? LCM of 2, 3, 5 will be 30. And if I take LCM of this, I hope, let's check. Okay, we will see what is LCM of this. Where is the given group? Yeah. LCM of yes, it will be still Z50 because LCM of 4, 12 and 5 is still, since these two have GCD1, this will be still 60. So that's why these two groups are equal. I will give you an explicit example where that's not possible. Let us do this. Let us first finish this one. Yeah, here the the LCM for the first example, the LCM of order of the exponent of this group G1 is exponent of, if I call this G1 or H1, this H2, this H3, and this H4, then exponent of H1 is LCM 3, 4, 3, 8, and 10. And LCM of this is LCM of 3, 4, 8, 10. And this is LCM of 3, 2 square, 2 cube, 2 into 5. This is 2 square, 3 into 5. Right. And this is what this is 60. And second one, exponent of this H4 will be this LCM. Let us check LCM of 2, 3, 4, 120. 2, 3, 4. Yeah, here it will be cube. 2, 3, 4, 120. It will be 120 because 2, 3, 4 all divide this group. So that's why this group H1 has, yeah, this H1 as H4 will be isomorphic to my G1 because both of them have exponent 120, which is equal to the exponent of G. And now let us move to, so for example, if I go here, the box which I wrote for, I think 100, and where is it? Yeah, this one. Here, if you check here, exponent of this one is 108. Here, exponent will be 9 4 za 36. Here, exponent will be 4 into 3, 12. Here, exponent will be 54. Here, exponent will be 18. And here, exponent will be just 6. Okay, so what we need to check for checking whether given group is isomorphic to the uh, groups in the options or not. First, we need to check the cardinality, and second, we need to check is the exponent of that group. That is where the key lies. Okay, when we were clubbing this in this earlier examples, when we were clubbing this Z3 cross Z5 and all those Z4 cross Z3, what we were doing at the end was we were keeping the, what I say, exponent of that group intact, and we were not disturbing it. Okay, and use this formula. Okay, I will just now color it for you. This, please keep in mind. This is what we are using here to check for the exponents. Because if my given group was So for example, let us go through this example itself. If I was asked what is the group which is isomorphic to any of this, and if I club a few groups, so for example, if I take this, let me write this in different color here. If I take this example, Z2 cross Z18 cross Z3. Okay, here the cardinality will still remain same, but which among these groups will be isomorphic to this group Z2 cross Z18 cross Z6, Z3? Only this one, right? Because here LCM of this 2 into 18 into 3 is 18. Okay, and none of the other groups have that exponent. If two groups are isomorphic, their exponent must be same, because if groups are isomorphic, every element match with the element there, and the powers of all the elements must match, and so on. Not this very, I mean, the order of element coincide. If I have element of order k in group G, if some group H is isomorphic to that group G, there exists some element of order K in that group. That's what isomorphism, I mean, that's what the property which we have under isomorphism of two groups. So if I take any other group, so exponent of this group becomes 18, because of the this earlier formula which I wrote. But if I say that if I club this one, so can I say that whether this group is isomorphic to this Z2 cross Z6 cross Z3 cross Z3? It won't be possible, because LCM of this 2, 3, this Z2 cross Z6 cross Z3 cross 3 is 6, and then exponent of this group will be 6. That is, every element in this group will become identity the moment I raise it to power 6. But in the given group, if I call this H1 and this H2, then it will be different. So that's what we need to do when we are checking the whether given group is isomorphic to the example, the group given in the example or not. Okay, please check. So I will explicitly write here. So to check whether given group G is isomorphic to group H of similar cardinality, what we need to check? We need to check the exponent of the group. Group G given abelian groups G is isomorphic to group H of similar cardinals. The moment I say that G is isomorphic to H and G is abelian, then H becomes abelian and of similar cardinality or similar order. Then we need to check the exponent of group G, whether the exponent of group G and H are equal or not. Okay, so this is how we will check for the isomorphism of groups of similar or abelian groups of similar order. First, check the order. The moment I have order, check for the exponent. That's it. Exponent of that group. If the exponent match, definitely those two groups are going to be isomorphic. That's yeah, that's the only way to do it. I will highlight this because this is really important. Okay. Okay, I hope this one was okay. If not, then I will move to next question here. And yeah, next question is question 6. That which of the following are true? And the options is that exponent of an abelian group is divided by order or order G for all G in G. Sorry. Any group of any group is a product of P groups. C is let G and H be elements of a finite group. Finite group G. Then order of GH is LCM of order of G, comma order of H, right? And the fourth part is none of the above. The first one, so let us start with one option, one at a time. Sorry. So exponent of abelian group is divided by the order of G for all G or not. So what is exponent of, so if I write this, exponent of exponent will be exponent of G is all those n in n such that smallest of n in n such that G power n is identity for all G. And what they are saying is whether this divides is divisible by order of G or not. So note that order of, if for G in G, order of G is smallest such that, g power n order of g, such that g power order of g is identity, right? And let us call this exponent as some nice number. Let us call this epsilon, the exponent. And this exponent is such that g power epsilon is identity. And we know that if I have some number dividing g power, so this by definition, so this implies that order of g definitely divides. This is for fixed. Let me write this word fixed here. Order of g will divide this epsilon, right? Because this is just some another number which is giving me g power epsilon is equal to e. Okay, so this is by order property. This we know. So this and this holds for, this is true for all g in g, right? This holds for every g. This g power epsilon is such that this epsilon is such that g power epsilon becomes identity for every element g in group G. And by what we have learned so far, that if some power of given element becomes identity, then that number is anyway divisible by order of that element. So that's why therefore we get that. Therefore, this is true for all g. Therefore, the order of g divides epsilon for all g in G. And that's what we wanted to check, whether exponent of an abelian group is divisible by order of G or not. So yes, it is divisible by order of G. Yes, I mean divided by divisible by same thing. So this first one is correct. Now the second option, that any group G is a product of P groups. So P groups is what? P groups means the power of P. I mean, let me just show you what P groups is. P group is just a group which has power P order. Okay, so that's what P groups is. So P group is, wait. P group is the group such that each element of that group has order P. That's P group. So P group is group where each element has order P. That's P group. And what here asked is that any group G is a product of P groups. And we just saw in structure theorem that every group there, we could write it as product of P groups. Okay. And yeah, so no, I mean, not product of P groups, but not product of P groups, but yeah. Here the question is that given any group, whether it is a product of P groups or not. Okay, so for example, consider this. This was my A. So B is this. So we can take this simple example. Q8. This is E I J K. This is generated by E I J K such that I square J square K square is E and Ij is K and Ij is equal to minus Ji. This is enough to check that. Okay, so this is Q8. Okay, and if I want to write it as a product of P groups, then the only possibility for Q8 will be we don't even have to go there. Okay, when we write product of P groups, they will be abelian, right? Because wait. Let us just check whether we can write it. So Z2 cross Z2 cross Z2 is a possible P group which we have. But this is abelian. And again, and if the other possibility for this will be Z4 cross Z2, right? And this will again be abelian because Z4 is abelian and Z2 is abelian. The direct product of two abelian group is abelian. So this is not possible. Again, this won't be possible. So the non-abelian groups cannot be written as, we can't write them as product of uh, P groups. Okay, we will again check for this one. Yeah, this one is not possible. So if I have cross product of P groups, then it has to be abelian, and then that's not possible. In here also Z4 cross Z2, I have any element of order. There are what I would say is there are yeah, there are four elements of order 4 here, but yeah, this one bar, no, one bar, 3 bar, 1 bar. There are only two elements. These are the only two possibilities of order 2 elements in Z4 cross Z2 because yeah. But here there are 3 elements of order 4, minus I, minus j, and minus k. So therefore this is not possible by order also, by exponent also. So exponent, yeah. So understand that Q8 cannot be, this quaternion group cannot be written as the product of two P groups. We will again come back to this tomorrow. We will also be having session tomorrow. So we'll come back to this tomorrow again if there are any ambiguity in this. Otherwise we will move to this next option that let G and H be elements of a finite group G, then order of GH must be equal to order of G into order of H. So the first thing you can check here is that what they are saying is that G and H are any two elements of group G. They have not given any condition on this G and H. Okay, so if I choose, first thing is that if we choose this G in G such that order of G is some K, okay, then note that we also know that if order of G is K, then order of G inverse will also be K. We know that, this we know. Order of G is order of G inverse will be, this is non-identity. If I take some K, and since this is non-identity, K will be something greater than 1. And yes, so order of G is order of G inverse. So by this, order of this, let me write order here. Then order of G inverse will be LCM of order of G into order of G inverse. So that is, let me write this, order of G into order of G inverse, which is LCM of K comma K, and LCM of K and K will be K. But what is this? This is order of identity, that is K. So this is contradiction, not possible. Not possible does not make sense. Okay, from the what notion we have for order of identity or the overall definition of order does not suit here. Okay, so that's why we get that this is not possible, that G and H, I mean, this is false. This is false, not true. And this is the logical argument which we can do with this given statement. Other than that, what we can do is you can just take any non-abelian group, finite non-abelian group, maybe Sn or any group of the Sn or other group, not other group. I mean, take Sn. Sn is non-abelian finite group. So any finite group will be isomorphic to some subgroup of Sn. This is a statement. Forget about that. Take Sn and take any two elements and swap them. I mean, and check whether the order of G and H will be equal to order of LCM of order of G and H or not. Check whether that happens or not. And you can take any two non-permuting cycles, or I mean, try to find explicit example using Sn. I will write that here. Try to find explicit example. If you can't find it using Sn, then we will discuss that tomorrow. Tomorrow, we are again meeting tomorrow for the meeting. We will again meet tomorrow for the interaction session, and we will again discuss few more problems that will be revision of everything we did, and we will try to cover as much as problems from various topics which we have discussed so far in the course. So yes, thank you.